Hey everyone, welcome back to my YouTube channel. So in today's video, we are going to implement a binary search tree in Haskell. Yes, a binary search tree. So if you're not familiar with binary search tree from languages like C, here's what they are. An element points to two elements, 3 and 7. They can be any numbers, not necessarily 3 and 7. One on its left and one on its right. The element to the left are smaller. The element to the right will always be bigger than the parent element. Each of those elements can also point to elements or one or none. In effect, each element has up to two subtrees. And the cool thing about binary search trees is that we know that all elements at that left subtree of say 5 are going to be smaller than 5. Elements in its right subtree are going to be bigger. So if we need to find if 8 is in our tree, we start at 5, and then because 8 is greater than 5, we go to the right. We are now at 7, and because 8 is greater than 7, we go to the right again. Here, and we found our tree element in 1, 2, 3 hops. Now, if this were a normal list or a tree but really unbalanced, it would have taken us 7 hops instead of 3 to see if 8 is in there. A really cool information I would like to share that sets and maps from data.set and data.map, if you're familiar with these in Haskell, are internally implemented using trees. Yes, trees. Only instead of normal binary search trees, they use balanced binary search trees, which are always balanced. But right now, we'll be implementing normal binary search trees. So without any further ado, let's get to coding. So here's what we're going to say. A tree is either an empty tree or it's an element that contains some value and two trees. And it should of course derive show so that we can print it out, read and equality type classes. Okay, good. This is good. Instead of manually building a tree, we're going to make a function that takes a tree and an element and inserts an element. We do this by comparing the value we want to insert to the root node, and then if it is smaller, we go to the left. If it is larger, we go to the right. We do the same for every subsequent node until we reach an empty tree. Once we reach an empty tree, we just insert a node with that value instead of the empty tree. In languages like C, if you're familiar, we do this by modifying the pointers and values inside the tree. In Haskell, however, we can't really modify our tree. Why so? Because Haskell is an immutable. So we have to make a new subtree each time we decide to go left or right, and in the end of the insertion function returns a completely new tree. But Haskell doesn't really have a concept of pointer, just values. Hence the type for our insertion function is going to be something like this. We are going to give it an element and a tree, and it's going to return a new tree with this element inserted inside it. Cool. So it takes an element and a tree and returns a new tree that has element inside it. This might seem like it's inefficient, but laziness takes care of that problem. So we're going to create two functions. First, we're going to create a singleton function, which is used to create a, what do you say, like a empty tree like that. So we are going to pass it an element. Sorry, not an empty tree, singleton. So like, and a tree with just a single element, which is going to be A. So we give it an element A, and it returns a tree which is which has only one node, which is the A element itself. So singleton X equals to node X, left subtree will be empty, and the right subtree will also be empty. Cool. So now we're going to write an insert function. So we call it tree insert. We're gonna make it. We pass it an element A and a tree, and it's going to return to us a new tree with the element A inserted into this tree. Okay, tree insert X empty tree. So in case a user passes an empty tree, and the next we can just return a singleton tree, which is nothing but a tree with only one element, which is X. So for that we have already created the singleton function. We utilize it over here. So it in fact turns out that singleton is a helper function for this tree insert function, but it can also be used alone. So tree insert, for other cases we're gonna code it up right now. Node A left right. So we're gonna be using guards because guards make our life a lot easier. And if X equals to A, then we simply insert it at this position. So node X left right. And if X less than A, we say node A. Because it is less than, we should traverse to the left subtree. So tree insert X left. So what we are happening is that we are returning a new tree, which is having the same right subtree, but the left subtree is getting modified with this function, which will take the left subtree and insert X somewhere inside the left subtree. And similarly, X greater than A equals to node A left, but here we insert inside the right subtree. Cool. So the singleton function, as I said, let me repeat one more time, is just a shortcut for making a node that has something, and two empty subtrees. In the insertion function, we have the edge condition as a pattern. If we reach an empty subtree, that means we are where we want, and instead of empty tree, we put a singleton tree with our element. If we are not inserting into an empty tree, then we have to check some things. First off, if the element we are inserting is equal to the root element, let's return a tree that's the same. If it's smaller, return a tree that has the same root value, the same right subtree, but instead of the left subtree, put a tree that has our value inserted into it. Same, but the other way around goes if our value is bigger than the root element. So what's pending? So we have to check how to check if an element is present inside a tree. So we're going to create a function called treeElem for that. First, let's define the edge condition. If you're looking for an element in an empty tree, then it's certainly not there. So first, let's create a type definition, treeElem. We're going to pass it an element and a tree, and it's going to tell us if the element exists inside the tree or not. So treeElem x empty tree is of course going to be false. Okay, notice this is the same as the edge condition when searching for elements in the list. If you're looking for an element in an empty list, it's not there. Anyway, if you're looking for an element in an empty tree, then we check some things. If the element in the root node is what we are looking for, great. If not, what then? Well, we can take advantage of knowing that all left elements are smaller than root node. So if the element we are looking for is smaller than root node, check to see if it's in left subtree. If it's bigger, check to see if it's in the right subtree. So let's code it up real fast. treeElem x node A left right x equals to A. We found our match, so true. If x is less than A, we should find it recursively inside left subtree. If x is greater than a, we try to find it inside the right subtree. Cool. So all we had to do was write up the previous paragraph in code. So let's have some fun with our trees. Instead of manually building one, although we could, we'll use a fold to build up a tree from a list. Remember, pretty much everything that traverses a list one by one and then returns some sort of value can be implemented with a fold. We are going to start with the empty tree and then approach a list from right and just insert element after element into our accumulated tree. So let's do it in a terminal instead of here. So I'm going to open up my terminal, open GHCI real quick. Let me load my main function, main file. So let me create a list called nums. You can have it. You can have any elements inside it. I'm gonna put 8, 8, 6, 4, 1, 7, 3, 5, and let's create a nums tree which is built from the elements in the nums. So we use fold r tree insert function to insert element by element. Accumulator will be an empty tree and from nums list. And let's print out the nums tree. Great, we got it. Remember, we are able to print it because we derived the show method here. If you don't derive the show here, the tree won't be able to the Haskell won't be able to display this like this. Okay, let's try out other functions like treelm. Let's use it as an infix function. Treelm tree. Great. And 100 is not present in our list, so let's try that. Treelm. So if you don't know, putting backticks lets you use any function as an infix function. If you didn't understand about the backticks, you can use the same function like this. See, these both are the same functions, just that treelm is an infix function over here and prefix over here. And let's try with 1. And 10. So checking for membership also works. So as you can see, algebraic data structures are a really cool and powerful concept in Haskell. We can use them to make anything from Boolean values and weekday enumerations, binary search trees, and many, many more. Follow my channel for more such videos. Thank you, and please subscribe to the channel.